So now that we're talking about atmospheric stability, stability is the resistance of the atmosphere to vertical motion. So we talked about the idea of air molecules and pressure before, and the idea that as you go higher in altitude, there's less pressure because you've got less of the air molecules weighing down on you. So when we're talking about stability, we're talking about that resistance to vertical motion. So the idea that air wants to rise, and so stability is that resistance to that rise. So if you have a stable atmosphere, that's suppressing vertical motion. If you have an unstable atmosphere, it encourages that vertical motion. And so this becomes really important due to the idea of fire behavior and smoke dispersion, because you think about it and think about the convective column rising from a fire. So if it's encouraging vertical motion, you can get a lot of rise, which means you can get a lot of air coming in to replace all that air that's leaving. But if you don't get a lot of rise, then air from coming in, which then starts to eliminate or really slow down that oxygen component, and now all of a sudden our fire can be a little more under control. Looking at this image that we have here on the right, as we go up or as we go from low to high temperature, we usually get unstable atmospheres with lower altitudes and lower temperatures, and we get stable atmosphere with higher altitudes, higher temperatures. So, going back to our basics, hot air rises, cold air sinks. And so if we think about just a basic sunny day, solar radiation heats the ground, heats the adjacent air, we've increased that movement of molecules. We talked about temperature before, how that just, if we get more heat, the temperature molecules the molecules start moving around, and they're moving around more, they move around less if it's not hot. So we get lots of molecule movement. So our heated air begins to rise, gets replaced by the cooler air, and they call that vertical mixing as that hot air rises and cools off. Also to note, our daytime air movement is usually upslope, and so it's just something to understand with the same idea that hot air rises and cold air sinks. So if our air is rising, then if we got topography in the way or whatever, it would still kind of go the same way in slope. And so why should we care about atmospheric stability, or why is it important to us? Well, in terms of fire behavior, these are the kind of things that will be helpful to know. So indicators of atmospheric stability. So if we got stable atmosphere, you usually see stratus clouds. We'll talk about clouds in a bit. Your smoke column will drift apart after limited rise. There's usually poor visibility, fog, steady winds, right? Instability. So you get smoke rising, you get the plume growing, you get cumulus clouds, you get upward and downward currents and gusty winds, you get good visibility, and dust devils are all possibilities in instability. My favorite atmospheric stability, though, is birds. Because if you watch birds, so if you think about the idea of just the winds, so stable atmosphere versus an unstable atmosphere. In the stable atmosphere, you've got steady winds. When you have instability or an unstable atmosphere, you get upward and downward currents and gusty winds. So if you ever look at birds, and you ever see a bird that just like opens its wings and it's just kind of sitting there and just kind of going back and forth, not doing anything, not flapping or anything like that, stable atmosphere. Probably going to be a day where fire behavior is not going to be as bad because it's nice steady wind. Whereas if that bird is working hard, if that bird's pushing, it's probably because there's a gusty wind or there's a current that it has to go against. And so that's probably going to be a sign that it's an unstable atmosphere. With the unstable atmosphere, we're much more concerned with that happening because you get an increase for spotting potential, and especially long distance spotting. So your firebrands can travel very far, and you get less predictable fire behavior because of the amount of that idea of the hot air rising and then pulling in more air and pulling in more air and pulling in more air. All of a sudden that oxygen component becomes really good. If the fire starts building steam and creating its own weather patterns and pulling in air with the updrafts, it can become really problematic. And so that's kind of the big takeaway with stable versus unstable atmosphere. So let's kind of break it down just a little bit more to see if we can make it easy. So stable atmosphere, you've got warm air sitting on top of cool air. The cool air near the surface doesn't rise, or if it does, it barely mixes with the warm air. In an unstable atmosphere, right down here, you got the warm air rises like normal, or what we would think of normal, because air wants to do vertical motion. And so the warm air rises up into the cool, cold air and then just keeps going. So how do you get this to happen? The instability. Orographic lifting. So in this case right here, we've got the mountains here, which can help push it up. If you have a front coming in, talk about that too. They can help out, and the jet stream. If you get the jet stream to be can send downdrafts basically from the jet stream that can kind of help speed this along, or updrafts into the jet stream actually that help pull that air up. The book uses a wood stove analogy, which I really like, and I think it's actually very easy for people to understand. Is a stable atmosphere is like having the chimney closed on a wood stove, right? The air tries to go up the chimney, but eventually it just hits us apart, and then it kind of has to stay there, whereas some of that air might still go through the chimney, but not a lot. The majority of it just kind of has to sit there. Whereas if you have that chimney open in a wood stove, the smoke just keeps going and going and going, and it rises and rises and rises, and nothing's there to stop it. So is it just like, well, today's a stable day and today's an unstable day? That's not really how it works. It's going to be a mixture of both. So the afternoons are usually the most unstable time of the day, whereas the most stable time of the day is overnight. And so one sign with atmospheric stability, or one thing that we get here in California a lot and deal with a lot, is inversions. And so an inversion is a very stable layer in the atmosphere in which the temperature increases with altitude. So normally, or what we think about as normal with vertical motion, warm air to cooler air. But with an inversion, you get cool air that then becomes warm air. So we talked about stability. So if you see an inversion, it's definitely a sign of a stable atmosphere. Like we said before, one of the signs of a stable atmosphere is fog, and fog is a definite sign of an inversion layer, where you basically have the air, instead of rising, it hits more warm air, and it's like, well, I'm not going to rise because, I'm rising because I'm going from warm to cool. If I'm going from warm to cool, or cooler to warm, I'm not going to rise. An inversion basically acts like a lid. Severely limits vertical motion. You can get nocturnal inversions quite a bit. The coldest air in an inversion layer will be at ground level, and temperature will increase with height. I mean, eventually, if you get high enough, you get up into the jet stream and all that, you'll eventually get over the inversion and get back to that cool air. But, oops. There we go. So, with inversions, how do they happen? Well, the solar heating, if it's a nocturnal inversion, the solar heating of the next day will break the inversion. But other than that, it might just be a change in the temperature. If smoke is released into an inversion layer, it will rise only until its temperature is equal that of the surrounding air. Then it'll flatten out and spread horizontally. If the smoke column isn't hot enough to punch through the inversion, if the smoke column is hot enough to punch through an inversion, you can get a real sudden and substantial increase in fire intensity. When an inversion break, you could get a change in winds in both speed and direction. You can get an increase in fire behavior. You'll definitely get an increase in temperature and a decrease in relative humidity. So here's a great picture of an inversion layer. So warmer air up here, cooler air below. So this smoke column goes up and then just flattens out because there's no reason for it to rise. Hot air rises, but if this air is hotter and this air is colder, then it's not going to rise because it thinks that this is where it needs to go. So it just flattens out along the inversion layer. So here's 4 examples of an inversion layer. So the one that we mentioned before, the nocturnal inversion, so nighttime or radiation inversion. You know, if we have our little fire here, it hits that layer and then just kind of sits there because this is this layer's warmer. You know, if it could get up here, that's cooler air and it'd keep going, but this is cooler, warmer, and it just kind of sits there. Frontal inversion, so if we have a front coming through, in this case, by the symbology here, it's a cold front coming through. Right here, following the front is an inversion happening. The one that we're most used to here in California is the marine inversion, where we get the cool, moist air coming in from the coast. We get warmer, drier air above, and then we get this, you know, layer of marine fog that we're used to, where people complain about the idea that, the Mark Twain quote of the coldest winter I ever spent was a summer in San Francisco, and that's because of this marine inversion. And then there's a subsistence inversion, so the idea that you have a high pressure system and you get this unstable layer below here, and then you just end up with this nice warm air here. So you got cold, or you got cool, cool, and warm, and you just get that inversion layer there. So wind's our next subject. So when we define wind is the horizontal motion of air. And so how do you get horizontal motion of air? Because the whole idea is that air does vertical motion, right? Well, that's caused by the uneven heating of the Earth's surface. So we get solar radiation from the sun, but not everywhere gets hit the same exact way because the sun's at an angle. Some places will be slightly hotter, slightly colder, and those slight little changes then cause that air, instead of just moving straight up, to then move from one spot to another, because remember, it's the idea of it going from warm to cool so that it can expand, or if it goes to warmer, then it condenses. And so that changing happening from that uneven heating then causes wind. How do we describe wind? So usually you'll hear wind described with a direction. So the direction is the direction which the air is coming from. So this example here on the right, if you have a northerly wind, that means that it's coming from the north. Now, what's interesting though is if you're talking ground direction, it's where it's going. So if somebody says like it's a down drainage wind, that means it's going down the drain. If somebody says it's an upslope wind, it's going up the slope. So I know that's confusing, but I don't know why they made that change. But so if you hear somebody on the weather report saying a northern wind, or a nor'easter, or an east wind, that's where the wind is coming from. Wind is the most difficult weather variable to forecast, and it changes constantly. And so I think a lot of people are like, oh, well, weather people don't know what they're talking about. It changes all the time. Yeah, wind does change all the time, and that's the hard part for it. It's really hard. You can predict based on seasonal patterns the basics of it, but there's all sorts of variables that can change it. Because remember, the wind is caused by uneven heating of the Earth's surface. So if you get just slight changes in temperatures and RH, you're going to get changes in the wind. And so it's just very variable. Once a fire is ignited, Wind is the most important variable affecting fire behavior. So it's absolutely critical to understand wind, because wind can change your fire completely. You can have gusts or changes. You can have changes, 90-degree changes, 180-degree changes. It's very unpredictable, but it's something you have to pay attention to and have to really understand if you're going to be dealing with fire behavior. Just to kind of give yourself some more information, the idea of the Coriolis, forced Coriolis effect, if you want to pause and watch that video right there, just to kind of give you a little bit more about wind works. So, slide myself over here. Wind can influence fire behavior. So how does it influence fire behavior? Well, rate of spread and direction of the fire are greatly influenced by wind speed and direction. Wind can accelerate evaporation and drying of fuels, which we talked about. And that's extremely important because we know that fuel moisture, that's a big deal in whether stuff is ready to burn or not. You can get flame tilt, so you can get wind bending the fire over towards unburned fuels. That causes that preheating through convection and radiation, because you know radiation is always happening, but if you get convection and radiation, now we got 2 out of the 3, and probably a little bit of conduction happening. So if you get all 3 types of heat transfer happening, that's going to make your fire burn faster, because you get those fuels preheated and dried out quicker. Wind, of course, is the supply of oxygen to the fire. We know that's one of our 3 parts of the fire triangle, so that's always going to increase our rate of combustion. And wind also then can encourage firebrand formation, and then that spotting potential where it could take it, miles away and still start more fires. So those are all big deals when we're talking about fire behavior and the effect of wind. The sea breeze, something in California that I think most of us enjoy. So the afternoon sea breeze near the coast is driven by land-warmed air rising and then the cool marine layer rushing in to replace it. Is this what leads to that marine inversion that we talked about before? Absolutely. The idea that we're getting that the land gets heated up because just thinking about albedo, because of the color of water, you're going to get less absorption of the solar radiation in the ocean than you are on land. So the land gets heated up much quicker. That air rises, and then the cold air from the marine layer is coming in to replace it. And so this leads to an acceleration of surface winds, which I think a lot of us enjoy, getting that nice breeze in the afternoon coming off the coast. So this is how it works. So you got the ocean here for us. You get cooler air here. The land heats up. This air goes. This air comes in, and it returns flow, and we just kind of get this pattern happening. But what happens here is that then that gives us onshore winds and in the afternoon and provides a nice breeze if we're not dealing with fire behavior. If we're dealing with fire behavior, then we have to think about the fact of what does that mean with more wind and gusts possibly coming in, and also then if you're on the coast, that could bring that marine inversion. So, sweatshirts at the beach type of a thing. Here's kind of a look at it with kind of painting the picture a little bit more. So we got the ocean, we got the land. Of course, there's no houses in this picture, so I'm trying to think of where this wonderful, magnificent place is with no houses on the coast. But you got your boundary of the sea breeze. So here, it's a little bit cooler because of that sea breeze effect. So it's 86 on the coast, but then where you don't get that sea breeze, it's 93, because that's that difference that you get because you get this cooler air coming in. You're getting this constant sea breeze effect that keeps it cool. So that's why with the coast, we're not that far from the coast. We're a couple hours from Ventura. But Ventura can be, 75 one day and it's 90 degrees over here. And that's not too surprising. And that's due to the inversion layer and due to this whole sea breeze effect. So I would encourage you right now to pause the video and click this link right here about how to read a weather map and a lot of these things that we're talking about so far, and then plus a little bit more of what I'm going to talk about here, because I'm really just kind of going to throw a few things at you. So terms that you might hear when somebody's telling you the weather. They'll talk about air masses. It's just a broad region of air with uniform temperature and humidity. You'll hear about fronts all the time. I've already mentioned fronts. Usually what you'll hear about is cold fronts and warm fronts. There are occlusional fronts or stationary fronts. Really, you'll just mostly hear about cold fronts and warm fronts. But all that is, it's a dividing zone between two of the aforementioned air masses. And so a front forms when the two air masses converge. And so the larger the temperature difference between the two fronts, or between the two air masses, the more you'll get higher wind speeds associated with the front. And so what are these air masses usually that you get these fronts between? Well, it's usually a high pressure system and a low pressure system. So a high pressure system is the air mass that usually follows a cold front, and the low pressure system is the one that follows a warm front. So with the cold fronts, usually it produces several good days of good burning weather. With a warm front, generally poor burning conditions. So let's take a look at a map here and see, can we apply what we're talking about? So these triangles, the triangle teeth, the blue, that's a cold front. The half circle red, that's a warm front. And so you see the L's, those are low pressure system. The H's are high pressure systems. So high pressure systems follow a cold front, right? Low pressure systems follow a warm front, right? And sometimes you can have the cold fronts and the warm fronts switch off. This one, out in front of this cold front here, we got rain and snow happening, thunderstorms happening out in front of this cold front, because remember, so the front is where you get the difference between two air masses. So because you're getting this difference in the two air masses, you're going to get some winds, you're going to get some change and some more of your erratic weather when there's going to be this change in the air mass. So let's take a look. So when we talk about fronts, so a front is a zone of transition between two air masses. The reason they don't mix is because there's different densities to the air masses. What's really important about fronts is it can lead to strong winds, wind shifts, which can really change fire behavior. Although it's not common in California during fire season, it's much more common during late fire season, during fall. But the other thing that's important is the idea of the buildup of thunderstorms. Because that, we know thunderstorms mean lightning, lightning means ignitions, and we know that's one of the big ignition causes for fire. Frontal zones represent the leading edge of a wedge of cold or cold air. If that cooler cold air is moving to warmer air, that's why they call it a cold front. If that wedge is actually retreating and the warmer air is pushing into the cooler air, that's called a warm front. So, I don't know if there's a good place to put myself. How about right here? Close enough. Okay, so just kind of gives you a little bit more on it to give you that idea. So, advancing cold air behind a cold front, so the front's moving that way. So wherever the teeth are pointing out, that's the direction it's going. So here's the warm air in front of the cold front. It's receding, and so it has to get pushed up because this is an air mass, this is an air mass. So one of them's going to push through and one of them's going to push up. And so with this cold front right here, we're getting cloud development because of the frontal lifting of the warm, moist air. And we're getting big development. Right down here with our warm front, we got our warm front symbol here, right? It's got the half circles, and whichever way they're pointing, that's the way it's going. So this is the advancing air behind the warm front, and it's pushing up. We're getting cloud development there as well due to frontal lifting, right? Because this is the receding cold air retreating and the warm air pushing up, because we still know that warm air wants to rise. And then we got little more definitions of it here, talking about the idea advancing cold air pushes under warm air and clouds form unless it's very dry. Warm front, less dense warm air slides up over the colder air, heavier air. The boundary is a long, gentle slope, and there will be wispy clouds. So let's look at it again, kind of get that idea. So here's a cold front here happening. Here's another cold front. Got some low pressure, some high pressure out here. Got some hurricane activity happening here. Just trying to get you guys comfortable with the idea that when you're looking at these weather maps, that it's not something that you can't understand, and that a lot of it is pretty basic once you know the language. So let's talk about clouds for a little bit. I would say right now, pause this video, click on this link, and check out that video about clouds. Here's just some examples on the left of some clouds. The one that's going to be really important to us is cumulus cloud development, because that's where you get a buildup of moisture and can eventually lead to the idea of thunderstorms. But if we see something like stratus clouds, these long wispy ones, we're thinking stable atmosphere, we're thinking no big deal. If we see cumulus development, if you think about a cumulus cloud, we're talking about it's got some vertical motion to it, the cloud itself, which means then we are allowing vertical motion, which means then unstable atmosphere, because we're allowing vertical motion to happen. So in terms of cold fronts versus warm fronts, here's kind of the differences we'll see in clouds and where. So we got this cold front here. We can see cumulus development happening behind it. We can also see cumulonimbus development happening in front of it, and that's where we're talking definitely thunderstorms, things that we want to be worried about. This warmer sector here, this is where we get some stability, because we see stratus clouds happening here. And then in front of the warm front, we can get some other types of stratus clouds, the higher up kind of stratus clouds happening there. And so it can kind of, just being able to look at the clouds can tell us kind of what we're looking at and what we can expect from the day. Thunderstorms. So we talked about that. Thunderstorms develop from cumulus clouds. So you got your three stages. You got your cumulus stage, where you're taking in updrafts. Basically, it's that whole idea, the warm air rising, with this because of the pushing of the air, you're getting air kind of coming up, and then it's being forced to condense together, and that's how we get this cloud development. In the second stage, the mature stage, that's where you can get the start of the rain and the lightning, because we're getting updrafts, and now we're also creating downdrafts too. In the dissipating stage, that's where we've got this full out anvil shape has developed, and we've got nothing but downdrafts, rain, and when we say downdrafts, we're talking about the wind, right? Updrafts, it's pulling up air. Downdrafts, it's giving off air. So in dissipating stage, we're getting lighter rain, because we've already kind of given off the big stuff. Could still be giving off some lightning at this point, but the mature stage, that's where it can get rough. You can get lightning up to 10 miles away on some of these storms. Gusty, erratic winds, change of direction. What's interesting is in California, depending on the time of the year that you get the thunderstorm, you could end up getting virga quite a bit, and virga is just rain coming from these thunderstorms, but it's so hot that it actually evaporates before it hits the ground, and then that's how you end up with something that people call dry lightning. And so usually you think about a thunderstorm and it's raining and you see the lightning and you hear the thunder, but sometimes you can get it to where you just get the storm part, but it's just lightning and thunder because there still is rain and there still is moisture coming from that because there always is, but it's hot, and so it actually evaporates before hitting the ground. In terms of wind, one of the things that's really important to understand in our area are Fern Winds. I know that's a different sounding word, but that's the terminology. It's a warm, dry wind that flows down the lee side of mountains. So not the windward side, the lee side. So not where the wind's coming from, but the other side. Definitely take a pause here. The Chinook wind, that's a name for a type of Fern wind. The most common ones that we have here are the Santa Ana winds. And so take a pause, watch this video. This Canadian weather person does a fantastic job. Canadian meteorologist, that's the right terminology, does a fantastic job of explaining a Fern wind. So Fern winds develop with stable atmospheres. You get high, what really happens is you get high and low pressures on opposing sides of mountain ranges, or at least in California, the orographic lifting part of it is very common to get these Fern winds. Why is it important to us? It can increase fire spread, but it won't last very long. So what's going to happen is you get a wind on the windward side. It blows up the slope, heated by sunshine. The moist air rises over the hills, cools, condenses into clouds, so it comes over here. And then now, once it's forced to rise up, now all of a sudden, same thing that happened before with the idea of this orographic lifting that we talked about. Now there's nothing there. That topography disappears. And now all of a sudden, the air on the other side is much drier. And so it's going to warm on this descent, and it's going to just kind of plow through here. And it's going to be a warm, dry wind on the leeward side of the mountain range. And so with fire spread, if you get this Fern wind, what's going to happen is it's going to come blusting through. You're going to have big gusts, can really change your fire behavior, but it's not going to last a really long time. This isn't something that, all autumn we get Fern winds. It just comes in, maybe it lasts a couple days, and then it goes away. So here's pretty decent explanations of how a Santa Ana wind, or if we're up in the Bay Area or the Sacramento Valley, a Diablo wind works. So the idea that what happens is you start off with high pressure in the Great Basin, and then the Great Basin sends east winds because they're east from us, so they're coming from the east, sends east winds, and they come funneling. They're basically trying to go from high ground to low ground, and they're going through the mountain ranges. And so what happens is, comes from Idaho, Utah, and the Great Basin, pushes to Southern California. We'll focus on the Santa Ana ones. So you get the high Sierra Nevada winds for us in the Central Valley block this all off because it's too high. They can't push over it. So no big deal for the Central Valley, for Bakersfield, Fresno, no biggie. However, LA and Southern California, they don't have those. Their mountains aren't as big. So now that wind can still, that heated dry air trying to make its way to the ocean, still can get through. So the desert, the Mojave Desert, Death Valley, all this, it still helps heat this wind as it's getting pushed through. So as the wind moves from higher to lower elevations and squeezes through these narrow canyons, that means it's heated up more and pushed to higher speeds. Finally, it breaks through in through the Santa Ana Canyon, but through all sorts of different passes and canyons through here. And then that heated dry air then comes and just tries to break for the coast. And so that's how you get those Santa Ana winds. And they can be very powerful and cause big problems in terms of fire. So the winds fan the flames, create turbulence and unpredictable conditions for firefighters. Another thing that you get with wind and fires are whirlwinds. So fire whirls are the kind of the smallest version of that. So those are updrafts caused by strong surface heating or heat from a fire. Stronger the updraft, stronger the vortex, which eventually could develop into a fire tornado. So if you want, take a pause and click on this video here where it explains the science behind a fire whirl, a fire tornado, especially looking at the one that happened up in Northern California on the Carr fire a couple years ago. Similar to a dust devil, if you ever seen a dust devil, where you just see the air kind of take up with an updraft and cause that vortex to happen. It's the same thing, but then fire comes with it. It really depends on the heating supply and the upward moving buoyant air. But what's important in terms of fire behavior is with whirlwinds, it has an unpredictable travel path. Sometimes it might just sit there and not go anywhere, and then sometimes it might take off, and they don't really understand it enough to know where that path is going to be. Here's some examples of fire whirls. So you get this updraft happening, and then with that updraft, you take fire with you. So there's just here's some more examples of different fire whirls. It seems like it's a pretty interesting phenomena. I have not seen a fire whirl in person. Closest thing that I've seen was more weird and much less dangerous. But I was driving across Highway 80 through Nevada, and I saw a dust devil like about 30 feet high of tumbleweeds, and I thought that was pretty interesting because it just went across the highway. So much less dangerous than a fire whirl, but similar phenomena. So basic California weather patterns then, because we talked about temperature moisture relationships, we talked about atmospheric stability, and we talked about wind. So how do we put this all together? Because people say, can't predict the weather, they try and all that stuff. We can get general patterns and general ideas, right? And if we look at it really long term, that's the climate. But in terms of general weather and patterns, during the summer, you're going to get a more steady state. You're going to get much more predictable behavior in terms of the weather. It's going to be onshore flow in terms of the winds, and if we're going to get that onshore flow, that sea breeze effect, that means that we're going to get a persistent marine layer along the coast. Going back to Mark Twain's coldest winter I've ever had is the summer in San Francisco. So we're going to get that persistent marine layer in the coast. You're always going to be rocking your sweatshirt at the beach during the summer. All right. Overlying temperature inversions divide the marine layer from the warmer air aloft, right? And so that's that marine inversion that comes with that marine layer. In terms of relative humidities, on the coast, it's going to be about 60%. So going back to that idea of relative humidity, we said that's the idea of how much water vapor is in the air. So a lot of wet water vapor in the air on the coast, 40 to 50% in the mountains. So about half of the water vapor it could have in the mountains. Inland valleys like the Central Valley and the smaller SoCal valleys, 20 to 30%. 10 to 20% in the desert. So during the summer, real high fire danger in the inland valleys and the desert areas, and depending on the day, up in the mountains. During the summer, wind is going to be less influential than relative humidity is on a given day in terms of fire danger, because that relative humidity is really going to tell us how much moisture is in the air and how quickly our fuels will will dry out in a fire. Our greatest fire hazard is going to be near summer solstice. Well, summer solstice, so that's the longest day of the year, which means that's the day we get the most solar radiation. We know that oxygen is already present, so that's going to be the hot, the day that we get the most solar radiation. So the fuels should be the driest that day, and then if it's a hot day, we get our fuel, heat, and oxygen mix. In terms of the fall, or autumn as your book calls it, which is a much more beautiful term, you get the jet stream migrates south a little bit, which brings more day-to-day variation in terms of our weather. Your fire danger will decrease because the days are getting shorter, less solar radiation, and you get cooler temperatures. But that doesn't mean that the danger goes away. You'll get higher relative humidities in the inland valleys and the mountains than you did in the summer because of those cooler temperatures. And you get changes in temperatures and pressure gradients that lead to those Fern winds, and that happens much more often in the fall. So that we transition to that September, October time. You get offshore flow, right? Because it's coming from the east, so it's going towards the ocean. That leads to those strong winds. Also leads to the lowest relative humidities of the season because it's drying it out, because it's a warm wind coming in and drying those fuels out. The Central Valley doesn't get affected by this because it's blocked by the Sierra Nevadas, but as a consequence, actually the Central Valley during this time is really stable in terms of the atmosphere, and that's how we end up with that Thule fog that we'll have to deal with sometimes in the fall. And so that's just kind of general weather patterns that we understand based on just this knowledge of how weather works. And so the last part I want to kind of leave you with is just specific fire weather interpretation. And so understanding that there's a California fire weather page, and you'll hear things like fire weather watch, or you hear terminology like a red flag warning. So if you want to pause the video here, click on the link in the lecture notes and check out the Southern California page. So a red flag warning. So what is a red flag warning? So it's issued for weather events which may result in extreme fire behavior that will occur within 24 hours. It's the highest form of alert that the weather system has. Extreme caution is urged, and the idea is that a simple spark could cause ignition and cause a wildfire. A fire weather watch is issued with weather conditions could exist in the next 12 to 72 hours. So red flag warning, it's supposed to be that next day, 24 hours. Fire weather watch in between a half day to 3 days out. The fire weather watch is one level below a warning, but your fire danger is still high during that time. So important factors. So if you want to pause here, I've got this fire weather factors, this NOAA link that you can check out. But important factors, not just for California, but just kind of in general. Temperature. Temperature is important. If it gets above 80, it's really important in terms of starting to think about it. But really, in California, because we can get up to 90 and 100, something to worry about. Relative humidity, anything below 30 becomes really, really worrisome. Wind speed and direction. You'll hear about surface winds. Those are 20 feet above the ground because they want to make sure that there's nothing in the way, like buildings and trees, for the most part. LAL is your lightning activity level, and then precipitation, because we're concerned about moisture with our fine dead fuels. And so those are kind of some important factors that they'll talk about in terms of fire weather. And so then just, now that you look at a picture of a fire here, and this is the last thing we'll talk about, it's not just, hey, look, there's a fire. Start thinking about things like, what are we seeing in terms of our rise? Are we seeing straight smoke rise? Because that would definitely be a sign of an unstable atmosphere. Well, it's rising, but it's also being pushed. So is it being pushed because the wind is really strong? And obviously the wind is pushing from this direction, from the bottom of our screen to the top of our screen. but is the wind strong and it's an unstable atmosphere because the smoke keeps rising, or is the wind strong and pushing, but then this smoke is actually going to hit a spot and then just kind of not lift as much, which means it's a stable atmosphere, which means even with the stronger winds, we're not going to get as erratic and as fast moving of a fire. It's trying to put all these things together, right? And then you'd be able to look and figure out what the temperature is, what the relative humidity is if you have a kestrel on you, which now thinking about it and getting to the end of this this talk, probably should have thrown that in there. But a kestrel is a pocket weather station that that firefighters will have with them, and we have one at Bakersfield College, and it'll measure wind speed, it'll tell you the RH, it'll tell you the temperature, and so that kind of gives you that quick clue right there of where you're standing. This is what the weather is. And so you'll be able to kind of put those ideas together with what you see, and you really start giving you a clue about what your fire is going to do, right? We can't totally predict exactly what a fire is going to do, but if we get a real good understanding of the weather, real good understanding of the fuels surrounding us, we can really start making better decisions in terms of trying to really understand, is it going to be a good fire, or is this something that we really need to get a bunch of people on and get out and really, really take care of?